Okay, so hello everyone, and thank you for attending today. I'm going to be talking about prefix sum or scan, and this is going to be one lecture in a two-part, in a one part of two lectures. In this lecture, I'm going to talk about a simple implementation of scan with some optimizations, and next time we'll talk about some more sophisticated optimizations. So to start, what is scan? So a scan operation takes as an input an array of elements x0, x1 up until xn minus 1. And it takes an associative operator. This could be something like sum, product, minimum, maximum, or any other associative operator. And it returns as an output array y0 to yn minus 1, where every element in the output is, and there's two versions of it. There's inclusive scan and exclusive scan. In an inclusive scan, every element in the output yi is going to be the operator applied to x0 through xi in the input. And in an exclusive scan, it's going to be the operator applied to x0 up until xi minus 1. So basically, for some element y1, I'm going to apply the operator to x0 through x1 for the inclusive scan, or just all the preceding elements, but not x1 for the exclusive scan. So, for example, in the case of addition, an inclusive scan would look like this. If I have an input array 3, 6, 7, 4, 8, 2, 1, 9, then the output will have 3 as the first element. The second element will be 9, which is 3 plus 6. The third element will be 16, which is 3 plus 6 plus 7, etc. And in the exclusive scan, the first element is going to be 0, which is the identity value of the addition operator. The second element is going to be 3, which is addition applied to the previous elements. In this case, it's just 3. The third value is going to be 9, which is 3 plus 6. The fourth value is 16, which is 3 plus 6 plus 7, etc. In general, in an inclusive scan, an element at position 3 is going to be the operator applied to x0 through x3. So x0, x1, x2, and x3. And in an exclusive scan, you're going to have the element at position 3 is going to be x0 through x2. So the operator applied to x0 through x2, but not x3. And of course, the first value here will be the identity value. The most common use of scan in parallel computing is usually the sum when you use the addition operator, particularly exclusive scan. And you see this, for example, if let's say you have different threads and every thread has a bunch of elements that it wants to place into some array. So maybe the first thread has 3 elements, the second thread has 6, the third thread has 7, the fourth thread has 4, etc. And they all want to partition this array so that they each know where they would put their elements. So what they can do is they can do an exclusive scan on the number of elements they have, and then each thread would know that it can place those elements starting at this particular index in some output location. So thread 0 would put its 3 elements starting at position 0, so it's index 0, 1, 2. And then the second thread would put its 6 elements starting at index 3. The third thread will put its elements starting at index 9, etc. But there are other useful use cases of other types of scans. So, for example, prefix minimum and prefix maximum have some uses in certain types of heap data structures, priority queues, and there are other kinds of uses as well. But this is the most common one. So to start, how do you do scan sequentially? So sequential scan is very easy, right? You just have a loop. If it's an inclusive scan, you have a loop. You initialize output 0 to input of 0, and then you loop from I equals 1 to I up until n minus 1. And in this case, output of I.
I just sorry to interrupt you, but I think your microphone might be picking up something unexpected, because your voice is breaking up quite a bit. Are you using your?
Try and move closer. Is this better?
This is infinitely clear. Yes.
Okay. So yeah, I'll try to be closer to the mic. So yeah, and then you look through the array, and for every element I, it's going to be the sum of output of I minus 1, which contains the sum of I minus 1 and all the preceding elements, plus input of I. In the exclusive scan, you will initialize the output you'll initialize output of 0 to 0, or whatever the identity value is for the operator that you're doing. And then as you loop from I to n, from I equals 1 to n minus 1, output of I is going to be output of I minus 1, which is the sum of all the elements before input of I minus 1, plus input of I minus 1. And in general, these would be the inclusive and the exclusive scan for kind of a general operator. Now, as you can see, sequentially, it's very simple, but there's a loop carry dependence here, right? Because every loop iteration depends on the previous loop iteration. So this isn't this embarrassingly parallel kind of pattern where you can just uh, have a thread do every loop iteration and they all work independently. There's clearly some kind of collaboration that needs to happen between threads, and there's something that we need to do to break this loop carry dependence. So how do we do that? So one thing to note is that when we want to do this, when we break this loop carry dependence and have these threads somehow collaborate, we're going to need to have some kind of synchronization across parallel workers. And you know that on GPUs, it's cheaper to synchronize between threads in the same thread block than to synchronize across threads in different thread blocks. So what we're going to do is we're going to use the approach of a segmented scan. So we're going to segment the scan. We're going to do a scan in different segments, and then we're going to combine the result of the different segments. So every thread block is going to scan one of these segments, a segment of the input, and then we're going to scan the partial sums of these segments, and then each thread block is going to update its segment with the scan partial sum. So let me illustrate what that looks like. So let's say I have this input, and I would like to apply a scan to it. What I would do is I would have every thread block scan a segment of that input. So now every thread block is going to have its own scan segment, right? Block 1 is going to scan this segment of the input to get this output, etc. And then what we want to do is here, the output of block 1 is missing the inputs that belong to block 0. So what we would like to do is we would like to take the sum of the elements of block 0 and add them to all the elements of block 1 so that we can get the final value. Over here, the result in block 2 is missing the sum of all the elements that belong to block 0 and block 1. So we'd like to take the sum of the elements in block 0 and block 1 and add those to block 2's output elements, etc. So what this actually is another scan, right? Because block 1 wants to add this last value in block 0 to its elements. Block 2 wants to add the last value in block 0 plus the last value in block 1 to its elements. Block 3 wants to add the last value in the output of block 0 and the last value in the output of block 1 and the last value in the output of block 2 to its elements. So what these thread blocks can do in this case is that each thread block can produce the partial sum of the elements that thread block was responsible for, and then we can scan these partial sums, and then each thread block can take the partial sum that corresponds to all the preceding thread blocks and add it to its own elements. So in this case, block 1 is going to take this value, which is the sum of all the elements for block 0, and add it to all of its elements. Right? Block 2 can take the sum of the elements of block 0, block 1, which is this value, and add it to all its elements, etc. Okay. Now, what we're going to do today is we're just going to focus on one thread block and how that single thread block is going to do a parallel scan of the elements that belong to it. Okay. So we'll focus now on implementing parallel scan in each thread block, and then we'll talk later about how we can do the combination. What I'm going to be doing in my code is I'm going to be launching I'm going to be terminating the grid, launching another grid that's going to do this scan, and then launching yet another grid that's going to do this addition value. But there are other ways of doing this, and we'll talk about those in the next lecture. But today, we're just going to focus on doing a scan within a single thread. Okay? All right, so how do we do a parallel scan within a single thread? So let's say I have the elements x0, x1, x2, x3, x4, x5, x6, and x7. So these are 8 elements, and these are to be scanned by a single thread block. Now, one thing we could do is we could do many reductions, right? We can do a reduction for each one of these elements, or at least for some of them, and somehow get the other values as a byproduct. So let's see what that would look like. So let's say I do a reduction for this last element to get the sum of all the elements. what I would do is I first do a reduction. So I'd have a thread add x0 to x1, another thread will add x2 and x3, a third thread will add x4 and x5, a fourth thread will add x6 and x7. Okay, and then they'll write them back into the same array. So this illustration down here is just the same array after I've done this part of the reduction tree. And I keep doing that. I do a reduction tree. I assume people here are already familiar with reduction trees. Okay, until I get this final value, which is the sum of x0 to x7, which is the value that I want. And also as a byproduct, I also got these other values, x0 to x3, x0 to x1, and x0. Okay, so I have as a byproduct, I have some of the values that I need in my final output, right? In the third position, I have the sum of x0 to x3. In the second, in position 1, I have the sum from x0 to x1. But I don't have these other values. These other values are incomplete. So what can I do? Well, since over here I would like to have the sum of all the values from x0 to x6. So I can do another reduction tree to get this value right here, right? So that would look like this. So here, what I'm saying is a parallel reduction tree gives me the last element, but also gives me, as a byproduct, some of the other elements that I need in my output. I can do a reduction tree to get x6. So that would look like this. And as a byproduct, I'm also getting the sum from x0 to x2 in this position. I'm still missing these two values, so I can do a reduction tree for this value right here. And I can do another reduction tree for this value right here. Okay, and by doing these 4 reduction trees, I end up with all the values that I want. Now, of course, it doesn't make sense to do all these reduction trees one after the other. What I can do is I can overlay all of these reduction trees and do them all at the same time. And that would look like this, right? It would end up looking something like this, where in the first iteration, I'm having for every pair of elements, right, I will add them and produce that result. In the second iteration, I'm going to have for every element, I'm going to add the elements that are 2 before it and write that to the output. And in the third iteration, I'm going to have for every element, add the element that is 4 positions before it and produce that as the final output. So this is an overlay of many different reduction trees. Okay, and this is called, or we call it in the book, the Koji Stone approach, because it's kind of similar to something that the Koji Stone adder design does. Okay, so how do we parallelize this? The way that we can parallelize it is we can assign one thread to every element in this array that we are applying scan on. And in the first iteration, each thread will be responsible to add the value that is 1 before its element to its element. On the second iteration, it's going to be responsible for adding the value that is 2 before its element to its own element. On the third iteration, will be responsible for adding the value that is 4 before its element to its own element, etc., until we get the final result. Okay. Okay, so let's go and implement this. But before I implement this, let me talk about one optimization that I'll do while I'm implementing this. Is these elements, these input elements, are in global memory. We will be reading them from global memory, and these output elements, eventually I want to put them in global memory as well. However, it doesn't make sense to keep reading and writing from global memory. So what we're going to do is I think people here are already familiar with shared memory. So we're going to bring these input elements into shared memory, put them in a buffer, and then we're going to do these successive operations in that shared memory buffer, and then we'll write out the final result to the global memory. Okay. So as an optimization, we're going to use a shared memory buffer to perform successive. We'll read from that buffer, do the additions, write to that buffer, etc., etc., etc. Okay, so let's go and implement this and see what that looks like in input. So over here, I'm not doing things 100% from scratch. I've already written some host code to allocate data and copy data over to the GPU, and then copy the result back and test it, compare it to a sequential version, make sure the result is correct. What I'm going to be focusing on is just the kernel. Okay, so we're going to have the scan kernel. The scan kernel takes an input array, which is the array of values that I want to scan. It takes an output array, which is where I would like to put my final result. It takes a n, which is the size of my input and output arrays. And it also takes this array partial sums. And remember how I told you how each thread block is going to produce a partial sum, and then we're going to scan that, and then we're going to go and add it back. So here, every thread block will place its partial sum in this array so that we can do that. Okay. I'm not going to talk too much about the host code. The host code is basically launching this kernel, and then after terminating this kernel, it launches another kernel to scan the partial sums, and then goes back and adds the partial sums to the elements of that thread block. So we'll be focusing on just the scan inside of a single thread block. So how do we do that? Well, first, we need to go and load these input values that the thread block is responsible for from global memory to shared memory. Okay. Now, every thread block is going to be responsible for one element in the input. So the first thing the thread is going to do is, every thread is going to be responsible for an element. So the first thing the thread is going to do is it's going to identify what element it's responsible for. That's going to be the element that corresponds to its global index, right? So the thread is going to find what its global index is. So we do that by saying unsigned int I is equal to blockindex.x times blockdiv.x plus threadindex.x. I assume that people are familiar with how to find the global index of a thread. Okay. Next, what we're going to do is we need to allocate a buffer in shared memory so that we can load the values from global memory to shared memory, so that we can do our scan inside of shared memory. So I'm going to allocate that statically, and for convenience, I've just defined the block dimension as a macro. So I have 1,024 threads per block. So the block is going to be responsible for 1,024 elements. I'm going to allocate a shared memory buffer that's 1,024. This is not the best way to do this. It's better to use templates where you would pass this constant as a template parameter. And it's probably better to use templates also for this type rather than having float to have some type T. The reason I'm doing it this way is it's usually simpler for kind of a first-time user to kind of follow along with this code than to complicate the code with a lot of templates. But the proper way to do it is by using templates to make the code more general. Okay, so I'm going to declare a shared memory buffer that's block dim in size. So we do that like this. So shared float. I'm going to call it buffer underscore s. You can call it anything you want. I like to use underscore s just to remind myself in the code that this is a shared memory object. And then we can just use the block dimension. Okay, so we've allocated the buffer. Now what we want to do is we want to load, every thread is going to load the value from global memory to shared memory. So we're going to have buffer underscore s. So thread 0 is going to place its element in position 0 in the buffer. Thread 0 in the block, I mean. And thread 1 in the block is going to put its element in position 1 in the buffer. So we're going to index the buffer using the local index of the thread inside of the thread block. Okay, so we're going to write buffer underscore s of threadindex.x is equal to input of I. Right here, I is the global index of the element inside of the global array. All right, so now every thread has loaded its value and placed it in a shared memory buffer that corresponds to its local index position in the thread. Now, after we do this, we need to make sure that all threads wait for each other to load the input values before they proceed to doing anything else. So we're going to follow this with a same threads. Okay. So now we've loaded this input array from global memory to shared memory. Every thread block has loaded its own segment in the global memory to the shared memory. Next, what we want to do is we want to do this overlap reduction tree kind of pattern. So how do we do that? Well, we notice here that in the first iteration, our stride, the stride being the delta, how much away a thread is going to go and grab a value, right? Here, every thread goes one before it's the element that it owns to grab the value from there. Over here, we move to a stride of 2. Over here, we move to a stride of 4. And we're going to keep doubling that stride. So we're going to go stride 8, and then stride 16, and stride 32, and we're going to keep going until we reach a stride that takes us halfway across the whole array. right? So if my array is block dim in size, then my final stride is going to be block dim over 2. So what we will do is we will go from stride 1 to stride 2, and we'll keep multiplying by 2 until we get to block dim over 2. So we're going to write that loop. We'll do for unsigned int stride is equal to 1. Stride is less than or equal to block dim over 2. And then every iteration, we're going to multiply the stride by 2. Okay? So we're going to keep doubling the stride until we get to block dim over 2. Now, what do we do in this case? What we're going to do is we're going to have every thread go get the element that is stride before it and add it to its own element, the element that it owns, right? So here, thread 7 is going to go and load the value at index 6 and the value at index 7, add them, and then put them at index 7. Okay? So we can do buffer underscore s of thread index.x plus equals buffer underscore s of thread index.x, excuse me, minus stride. Okay? Now, there are many mistakes I've made here, and I will kind of walk through them one at a time to see what are the things that we still need to get right. Okay, so first, this is fine. However, we have an issue here, which is that some threads, so thread 0, for example, should not load anything from behind it, from before it, right? Because thread 0, its value is already complete, and there's nothing at 0 minus stride, right? That's just going to be an out-of-bounds access. So we need to make sure that, same thing on the next iteration, both thread 0 and thread 1 should not load anything before them. So we need to make sure that we have some kind of boundary check to make sure that none of the threads go out of bounds, right? I think somebody's raising their hand. How can I allow them to answer to?
Yeah, so how about like maybe we just like do a Q&A like near the end because like I just like have no idea if this is a hacker or not at this point. So like I'd rather we be conservative just for this lecture.
Okay, sure. Okay, so we'll take questions at the end. I'll be happy to take all your questions at the end. Or if it's something that is extremely necessary for like understanding and moving on, let me know. Maybe you can write it in the chat or something, and I'll be happy to answer.
Oh, yeah. So folks, so on Discord, we have a lecture Q&A like text channel. So if you post any questions there, I'll be sure to read them and interrupt as that if they're interesting. Yeah, and then also Byron mentioned there's also a chat right here in Zoom as well if people want. So we'll be monitoring both.
Okay, great. So I will not keep an eye on the chat then. Maybe I'll rely on you to kind of let me know if there's a question to ask.
Sounds good, yeah.
Okay, great. Okay, so to do this, so back to what we're saying that we need to make sure that in the first iteration, thread 0 is not going to go out of bounds, right? Next iteration, thread 0 and thread 1 should not go out of bounds. On the next iteration, threads 0, 1, 2, and 3 should not go out of bounds. So how do we do this? Well, we notice that when the stride is 1, thread 0 is the only one that should not be accessing out of bounds. When the stride is 2, thread 0 and thread 1 are the ones that should not go out of bounds. When the stride is 4, thread 0, 1, 2, and 3 are the ones that should not be computing. Okay, so basically, it's when the thread index is less than the stride, right? Those threads should not compute, because if they try to compute, they're going to go out of bounds. So we need to make sure, if we get back to our code, what we need to do is we need to make sure that only the threads that are whose index is greater than or equal to the stride will compute. So we can do that by having an if statement right here, where we say if thread index dot x is greater than or equal to the stride. Okay. Another way to think of this is I'm accessing buffer underscore s by using thread index.x minus stride right here. So this value obviously has to be greater than 0. And the way to check if this is greater than 0 is by checking if the first value is greater than the second. This is a rule of thumb whenever you're writing CUDA, right? Or even any kind of parallel code. Every memory access that you do should have some kind of condition that's guarding to make sure that you don't go out of bounds for that memory access. So that's one way I debug my code to make sure I don't go out of bounds. I go to every memory access and I try to match it with some if statement or some loop bound that makes sure that this value is not, this access is not going to go out of bounds. Okay, so after I do this, I can do async threads. Okay. There's still a mistake that I need to fix over here, but let me finish the code and then I'll come back to it. Okay, so now that we've finished doing all of this, right, we have our final result over here. Okay. Once we have our final result right here, what we want to do is we want to take that result and we want to put it back. We want to put it in global memory. Okay. So we're going to come down here. And we're going to have output of I is going to be equal to buffer underscore s of thread index.x. Remember that every thread has the value that it's responsible for at position thread index.x in shared memory and at position I in global memory. Okay, so we just take the value from shared memory and we put it inside of global memory. Okay. We also need to make sure that the thread block writes its partial sum to the partial sums array. So in this case, we only need to have one thread in the thread block do that. It can be any thread. The thread that wrote that partial sum to global memory is this final thread. So kind of it makes sense to use the final thread to write it out, but you don't really have to do that with any thread. So here, I'm going to make sure only one thread writes that final value to the partial sum. So the way we do that is by having an if condition where only the final thread will enter that if condition. So we can write if thread index.x is equal to block dim -1. Okay, so if I'm the last thread, I will take my value and I will also write it to the partial sum of the block. So here, partial sums of block index.x is equal to buffer underscore s of thread index.x. Okay, so we've taken the value that the last thread produced and we've also written that to our partial sums. Okay, so this is a scan kernel modulo some kind of some mistake that I have here. Normally I have an interactive session in my class and I try to have them guess what is the mistake that I've made. But I think here we're trying not to have any too much interaction because of the security issue. So let me go and explain what the problem is here. So this access right here is incorrect, and the reason it's incorrect is because we have a race condition. A race condition is a condition that happens whenever you have multiple threads accessing the same memory location, and one of that accesses is a write. Okay, if I have multiple threads reading from the same location, we don't have a race condition. But if I have multiple threads accessing and one of them is writing and another one is reading, or multiple of them are writing, that's where we have a race condition. And that's exactly what's happening on this line right here. So let me illustrate what that race condition is. So if we look at what's happening here, the thread in green, thread 2, is reading the value x1 to add it to x2 and produce that final value. However, thread 1 in orange is also reading x1. And what it's doing is it's adding it to x0, but it's writing the result of the addition back into that same memory location. Remember that here in my illustration, these are all the successive versions of the same array. Okay, these are all buffer underscore s. So what could happen is if thread 1 reads x1, adds it to x0, and then writes out the value x0 plus x1 to this location before thread 2 reads that value, what's going to happen is thread 2 is going to end up reading x0 plus x1 instead of reading x1. And it's going to have the wrong value. Now, to get around this, what we need to do is we need to make sure that all these threads finish reading before any of them write. Okay, we should have all the threads finish reading before any of them write. To do that, we're going to have them all read, and then we do a sync threads to make sure they all wait for each other, and then we're going to have them write out their values. So I'm going to go back to my code right here. Okay. And what we're going to do is we break this apart. So this is actually buffer, instead of doing plus equals, I'm going to write this as equals buffer underscore s of x plus buffer underscore s of x minus, right? Okay. So what I want to do is I want to read these. I want to do a sync threads, and then I want to write the result over here. That way, nobody writes to the buffer before anybody reads that value. Okay, so we're going to break this apart. I'm going to declare a temporary value. I can call it temp, right? And then I'm going to write temp equals buffer of x plus buffer of x minus, right? And then I need to have a sync threads, and then I will do this buffer equals temp. Okay. Now we need to have a sync threads in between these, but I can't just put a sync threads right there. And the reason is that over here we have a not all threads in the block are going to enter this if statement. It's only legal for me to put a sync threads where all threads in the block reach that location. Otherwise, the behavior is undefined and the compiler can do things that are undesirable. Okay, so what we need to do is we need to close this if statement, right? Do the sync threads and then open it again. And we'll do it this way. I'm going to move temp outside. I'm going to close the if statement, right? I'm going to have the sync threads, and then I'm going to open the if statement again. So here what we're yes.
Do you mind if we take two questions? Is there some
Sure.
interesting chat? Yeah. So the first one is basically so Trevor is saying that as opposed to sort of manually reasoning about out of bounds memory accesses, they found that the compute sanitizer is helpful. Have you used it and have you found it helpful in your code?
Yes, of course. I mean, yeah, compute sanitizer is definitely very useful in helping you find bugs helping you find bugs with related to out of bounds accesses. Sometimes when you write a lot of code, it really doesn't take much effort to kind of just look quickly at each one of your memory accesses and make sure it matches up. That sometimes can be even faster than closing, running with your compute sanitizer, and then coming back and checking. But yeah, for the more tricky ones, of course, the compute sanitizer is a very useful tool, and I do recommend it.
And the second question is, if all the threads are executing the same SIMD instruction, how is it possible that one writes into the memory before the other reads it in a single iteration?
Okay, so that's a good question. So first, remember that these are all threads in the same thread block. So some of them can be in different warps. So this could be here, but the boundary between two different warps. So this one could be in one warp, this one could be in another warp. So this one could read and write before this one even gets scheduled. So that's one. But then the other thing is that even for threads in the same warp, there's no guarantee that they. So even though they're in SIMD, right? The compiler can do certain optimizations where it reorders memory instructions and it might promote stuff from memory to registers. The compiler can do all kinds of things, so the sync threads helps to create some kind of memory fence as well that makes sure that things are in memory when we expect them to be in memory. That's the second thing. So there's no guarantee that they will all, read from memory and write to memory in the order in which you specified in the code. And then the other thing is that from the Volta architecture onwards, the threads in the same warp, there's something called independent thread scheduling, where threads in the same warp are not necessarily in sync. You can have, I don't want to get into independent thread scheduling. I think it's a sophisticated topic for this lecture. But yeah, there's no guarantee that these threads will actually kind of read them from memory and write them to memory and always be kind of in sync with each other in the same warp. And that's why you should never assume in your code that threads in the same warp will be executing in SIMD, even though they do in many cases. So in your optimizations, you can be aware of the fact that they execute in SIMD, for example, like avoiding control divergence, but you should not assume that because the programming model doesn't guarantee that.
Yeah, excellent. Thank you for the explanation.
Okay. So yeah, so this is how we get around this race condition. Okay. So we'll wait for everyone to read, and then before we update and we write. Okay. So this here is the code that we just coded together. I'll include in the slides as well, and I'll be happy to share the slides after the lecture. They're also publicly available on the textbooks website. Okay, great. So we have this code now. I'm just going to run it and make sure that it works, just so that so here I can compile it. And we do have a bug. What's supposed to call this? Okay, and I'm going to run it just so we get a sense for how long this is. So here I'm doing a scan of an array that's 2 to the power 25 in size. So we're talking about 32 million elements. And there's 3 kernel launches because you have the scan, and then you have the scan of the partial sums, and then you have the scan of the partial sums of the second kernel, and then this is how long they take successively. I'm just trying it here so you can get a sense for the latency. So you're doing 32 million elements in 0.89 milliseconds. This is a voltage GPU that I'm using, and also to show you kind of later on when we apply an optimization and what the performance is. Okay, so going back. So we needed to add the second sync threads in order to make sure that we don't have any race conditions. But these sync threads have latency, right? They incur latency, and especially in this kind of computation where you don't have a lot of compute going on, your ALUs are not super busy, right? This operation is latency bound. You have a lot of these stalls in your pipeline. So having 2 sync threads inside of your loop is really an expensive thing, and ideally you don't want to have to sync so many times. So what we observe is that this second sync thread right here, this one enforces a true dependence. A true dependence is basically a read after write dependence, right? Because over here we need to have the threads to finish writing to buffer underscore s before on the next iteration these threads read from buffer underscore s, right? Because we need to wait for the value to be written before we can read it and use it. So this is a true dependence. We really need to wait because we need the value. On the other hand, this second sync threads that we had to introduce over here, this one enforces a false dependence. And what do I mean by a false dependence? This is enforcing a dependence that is a write after read dependence. What do I mean by that? It means that I cannot write to the location before everybody finishes reading from that location, right? I don't need people to finish reading from that location for me to make progress in my computation. But I need for them to finish reading before I write because I'm using the same buffer, right? It's a false dependence. The dependence is only there because we're using the same memory location for different things. If I was not using the same memory location, then I can write and others can read and I would not have to wait for them. So the sync threads enforces a false dependence. And what we can do to avoid the sync threads is to eliminate the false dependence by eliminate this situation where I'm using the same buffer. And this is a common optimization we use all the time in computing. It's called double buffering, or more in general, multiple buffering. So what we can do is we can have different buffers for the input and the output in every iteration of this scan operation. So here, for the first buffer, we can use buffer 1, and then we can allocate another buffer called buffer 2. And then when we do our scan, when we do our first iteration, we will read from buffer 1 and we will write to buffer 2. And in this case, when thread 1 reads x1, adds it to x0, and places the sum in the buffer, it's going to place it in a different buffer called buffer 2. And now I don't have to worry about thread 1 overwriting x1 before thread 2 reads it. And now I no longer need to have that second synchronization. Okay, but I don't want to have as many buffers as I have iterations. So what I can do is now, once I'm done with the first iteration, I no longer need buffer 1, so that I can go and use buffer 1 as the output of the next iteration. So, but of course, to do that, I need to propagate x0. So the threads that don't do any addition, now they actually do need to do something. They need to propagate their value because we need it at the end. Okay, so now what I will do on the next iteration is I'll use buffer 1 as the output, and I'll have the threads write their output to buffer 1, or the threads that don't do anything propagate their input to the output in buffer 1. And we keep doing that until we are done. So this is called double buffering, and it helps break the false dependence. So if we move back to our code right here, the way to implement double buffering is I will need to allocate 2 shared memory buffers and alternate between them in my scan code. So if we go back to this allocation right here, I'm going to duplicate this, and I'm going to have buffer 1 and buffer 2. And now the way I alternate between them is by creating a pointer, pointing that to each buffer, and then swapping the pointers every iteration. So I'm going to create a pointer, call that in buffer, and I'm going to initialize that to buffer 1. And I'm going to create another pointer, and I'm going to call that the output buffer, and I'm going to initialize that to buffer 2. And then, oops, let me excuse me. Okay, and now what I will load to, instead of loading to buffer underscore s, which is no longer there, I'm going to load to the input buffer. So here I will load to in buffer underscore s. Okay. Now inside of my code, what I will do is I will load over here. When I read these values, I'm going to read them from in buffer underscore s. Right? And when I write this value, I'm going to write it to the out buffer underscore s. And now because I'm reading from this input buffer and I'm writing to the output buffer, there is no longer a need to wait until I finish reading before I write. So now I can eliminate the sync threads. I can merge these two if statements. And in fact, I no longer need the stamp. I can simply write out buffer is equal to in buffer underscore s of x of x plus in buffer underscore s of x minus 1. But of course, we should not forget that now that I'm using a different buffer, the threads that did not do any addition should still propagate their values to the next iteration. Okay, so what I should do here is I should have else. And then if you're not adding, you will simply propagate the value from the input. So I will simply have out buffer underscore s of x of x equals in buffer underscore s of x of x. And what that does is it eliminated the sync threads that was enforcing the false dependence. So now instead of having 2 sync threads in my loop, I only have 1 sync thread in my loop. Okay, and let's go and check how that impacts performance. I'm going to compile that. Oops. Oh, so down here, I forgot to swap the buffers. So I need to. So after doing this, I need to on the next iteration, what used to be out buffer becomes in buffer, and now in buffer is going to become out buffer. So I'm going to swap the buffers. So here I will write temp is equal to in buffer underscore s. In buffer underscore s is equal to out buffer underscore s, and then out buffer underscore s is equal to temp. Okay, so here I swap the buffers so that on the next iteration, what used to be the output buffer in the previous iteration becomes the input buffer on the next iteration. Okay, and then down here, where we have buffer underscore s and buffer underscore s, we're going to use one of the buffers. It's going to be the input buffer. because it's the output buffer of the last iteration, but I swapped it before exiting the loop. So now it's going to be the input buffer. So here we will use oops, we will use in buffer underscore s right here, and we will use in buffer underscore s right here. Okay, so this is how we would apply double buffering. I'm going to compile that. Still have an error. I think before we started, we were speaking about the dangers of coding live, is that you end up having to deal with all these errors. Fortunately, so far they've all been minor errors. So we compile, and if you recall our previous kernel without double buffering, the largest one took 0.89 milliseconds. So now if we run, right, we're down to 0.72 milliseconds. So we kind of shaved off. Run that again. I was expecting a little more. Okay, so 0.7 milliseconds. So we got, yeah, it's not a huge improvement, but a lot of times these kernel optimizations are really an accumulation of all these little improvements that you do to the code. But you can see how that second sync threads actually made a difference in our code, right? 12.5% of the time was, or 1/8 of that time was because of that sync threads that we had to enforce the false dependence. This is actually an optimization that does come up in many other situations. So, for example, if you're doing matrix multiplication or tile matrix multiplication, where you load a tile from shared memory and then you multiply it, and you load the next tile from shared memory and then you multiply, right? So if you want, double buffering is useful here because you can overlap the loading of one tile with the next. You can overlap the computing with one tile with the loading of the next tile by using different buffers for the one that you're computing with and the one that you're loading. So double buffering is common use optimization in different locations. Okay. All right. So this is the code that we wrote with double buffering. Okay. So let's do some analysis of this scan operation that we did. So here I want to define the idea of work efficiency. So we say that a parallel algorithm is work efficient if this algorithm performs the same amount of work as the sequential algorithm. Now, if we look at scan, sequential scan performed how many operations? It performed n additions, right? We iterated through an array of size n, and we did n additions, right? Or maybe n minus 1 additions, but it's order of n additions. Well, what about this Kojison approach? How many additions did we do? Well, if you think of a single thread block, right? Let me go back to the illustration. So if you think of what's happening here, over here in the first iteration, we have if n is the size of this array, so 7, we did 6 additions in the first iteration. That's n minus 1. On the next iteration, we did 7 additions here, n minus 1. We have 8 in total. Next iteration, we did 6 additions. That's n minus 2. The next iteration, we did 4 additions. That's n minus 4, right? And we keep going. So if we look at the total there, right? In the Kojison parallel scan, we have log n steps, right? Because every time we multiply the stride by 2, so that takes log n to finish the loop iterations, and we do n minus 2 to the power of the step operations per step, right? So that gives us n minus 1 plus n minus 2 plus n minus 4 up until n minus n over 2. And if you solve for that, that comes out to being O of n log n operations. So we went from doing O of n additions in the sequential scan to O of n log n additions in our parallel scan. Okay, so we're doing many more additions to accomplish this scan in parallel than we were doing in the sequential version. Now, if we have a lot of parallelism and all these additions end up happening actually in parallel, that's fine. This work inefficiency might be a price worth paying in order for us to get our parallelism. Okay. However, if we end up, with GPUs, if we launch too many thread blocks, more than what the GPU can handle at the same time, the GPU ends up running those thread blocks one after the other, right? So if we launch too many thread blocks and those the hardware cannot support all of these and ends up doing them one after the other, and we get some kind of serialization between thread blocks, then we would have paid that work inefficiency for no reason. So this algorithm is not work efficient, and if resources are limited, then the parallel algorithm could end up being slower for work efficiency reasons. Okay, so Mark, how are we doing on time? Do you want me to stop here, or do you want me to go a little over? I think because we were late in the beginning.
I
Um,
think it's as much time as you want, to be honest. Like whatever you're comfortable. If you want to save stuff for later, but if you want to keep going, because I think we lost like a good 35 minutes or something from the beginning. So it's up to you.
okay. All right. Let me do. Maybe I'll do maybe 5 or 10 more minutes, and then we'll stop there.
Yeah,
Okay.
we can stop with Q&A. That sounds perfect. Yeah.
Okay. Great. Okay. So there are other work efficient parallel scan algorithms that do less than O of n log n. And one of them we call it the Brent-Kung approach because it's similar to the Brent. It's similar to what is done in the Brent-Kung. Okay. So this is another way to do parallel scan that does fewer operations in total. Uh, what we can do is we can start by doing just a reduction. Okay. So we have reduction, another reduction. Sorry, we have the reduction iterations. We do a reduction tree, and this was our first tree that we saw when I introduced the Koji Stone approach. But instead of doing a lot of other trees in parallel with this, what we will do is we will do a few more operations to complete the elements that are still not complete. So one thing we observe is here I have the sum of x4 and x5, and over here I have the sum of x0 to x3. So what I can do is I can just add those together. So we call this the reduction stage, and then I can add these together, and now I have this value is complete. And then here, x4 is just missing. If I add x0 to x3 to x4, I'll get the value that I want. Same thing here, same thing here. So I can add those, and I get the values that I want, and now I'm complete. Okay. So instead of doing all those reductions in parallel with this other reduction tree, I can do much fewer operations, but it will cost me more steps. So this is good. So if I compare the Koji Stone approach on the left, and the Brent-Kung approach on the right, you'll notice that the one on the left takes fewer steps, but it does much more. It does many more computations, many more additions in each step. Whereas the one on the right takes more steps, but it performs fewer additions overall. Right? You can see the number of arrows that I have here is much more than the number of arrows that I have here. Let's actually do this analysis. So if we look, we said that Koji Stone does log n steps of n log n operations. So in the Brent-Kung approach, the reduction stage takes log n steps, and the number of operations that I do in the reduction stage over here, we have n over 2 plus n over 4 plus n over 8. So then that gives me n minus 1 operations in the reduction step. In the post-reduction step, I do log n minus 1 steps, and you can work it out. I do 2 minus 1 plus 4 minus 1 plus n over 2 minus 1, and I get n over n minus 2 minus log n minus 1. So if I sum the two, I do 2 log n minus 1 steps. So I'm doing more steps than the Koji Stone approach. However, if I add all these operations, I get 2n minus log n minus 2, which is O of n operations. So this other parallel algorithm does much fewer additions. It's more work efficient. However, it takes more steps. So the Brent-Kung approach takes more steps, but is more work efficient. So the question is, which one is faster? Is the Koji Stone approach going to be faster, or is the Brent-Kung approach going to be faster? Let me stop here as a cliffhanger, and maybe in the next lecture we'll implement the Brent-Kung approach together, and then we'll also do some advanced optimizations for the scan for scan engine. Okay. So I'll be happy to take any remaining questions now.
Thank you, Azad. This was really awesome. And everyone, please make sure to give like a big round of applause for Azad. Like, thank you for the super like well-researched content. I guess, yeah, like if you want to ask questions, like feel free to ask in the lecture QA chat or just like raise your hand. here, and we can let people on. I guess I'll start with the first question, which is that at least like before we started to get fancy with the scan algorithm, like at least like the naive version sort of like looked suspiciously just like what the reduction kernels looked like in the book. So I'm sort of curious, at least like within like high performance code, is it the case that like do reduction kernels even exist in like NVIDIA code, or are they implemented as a scan essentially, or not really? Or is it these two separate tracks? Like,
Well, you'll have to ask the NVIDIA folks what exactly they're doing. But so in many cases, um, in many cases, for integer data types, you actually have the warp level primitives that do reduction in just a single intrinsic, right? You just have one instruction, it just does a reduction in
interesting.
hardware. So that's if you're doing integers. I don't think it's there for floating point numbers. Um, but for integers, you can just do a warp level reduction with just one intrinsic. And then how you do the reduction across warps, I mean, you can do a reduction tree like this. Um, it also depends on your situation. Maybe you might do atomics in certain situations to do the reduction across the different warps. So it really depends on how many warps you have and what your particular situation is.
Gotcha.
Um, yeah.
All right, I'm monitoring chat like a moment. All right, I mostly see a lot of hearts. I'm like looking at questions still. Andreas, maybe a
So
question.
I wanted to mention something else. So sometimes when you also do reduction, you might be the particular operator that you might be using might be a little sophisticated. Um, uh, uh, but of course, I mean, so the reduction in cub is kind of templatized, and you can pass to it some sophisticated operators. But sometimes, depending on the shape of your code, um, it it it's sometimes just convenient to kind of implement your own reduction. Um, but again, that highly depends on your situation. Sometimes it's easy, it's kind of easy to formulate, easier uh, to formulate your reduction operation, um, depending on the operation itself that you're trying to do. You might have to do it yourself as opposed to having to rely on an intrinsic or something.
Um, I think I'm also seeing an interesting discussion around like we have Jack asking, is Brent Kung related to the Belloc scan?
Um, yeah, I believe I think so. I know that there are other names that are used for Kojistone and Brent Kung in parallel computing literature. So I think so. Yeah, I think that there you might have it. There might be another name for this in the literature.
Another question from Andreas, like, are we going to discuss bank conflicts in the next session? Is this still an issue on current hardware?
It was a much bigger issue in the old hardware, and the newer hardware, the bank conflicts are not as big of an issue. Um, we do talk about bank conflicts in a different lecture. By the time we get to this material, we assume that kind of people are already familiar with bank conflicts, so we don't keep covering them. So no, we will not talk about bank conflicts in the next lecture.
So Brian Muhia is asking like what happens when the data doesn't fit in the powers of two? Does one expect some sort of sequential scanning in that case? And then Byron is asking perhaps padding is the solution.
Yeah, you can. So remember here we're the scan that we're doing is for a single thread block, right? And then you're gonna have many thread blocks. So only the very last thread block is going to have a segment that may not be a power of two. And in that case, you're going to have some kind of boundary condition where you can just pad with zeros. You don't have to pad the actual input. You can just pad when you're loading. So if I switch back to the code, so this code right here, I didn't include the boundary conditions for the sake of time, but you would have a boundary condition right here where if I was kind of out of bounds, you would just load a zero.
Mhm.
And then and then when you're writing it back out, you wouldn't write it out. So yeah, if your input is not a multiple of the block dimension, you can just have these conditions over here to do padding on the fly. You don't even have to pad the actual input.
I see two more people typing questions, Inu and Slacter. So Slacter is asking, he wonders whether scan can be generalized to 2D or 3D tensors.
Uh, that's a good question. It's not one that I've thought about, but it's certainly a good question. I think, yeah, yeah. I mean, I think you can probably generalize it, yeah, but it's not something that I've thought about.
Okay, I guess we'll throw this as homework to Slacter. If they're interested in generalizing it, I'm sure Izzat would be happy to review the code. All right, I think I see two more questions. Thomas. Oh, so Thomas is suggesting that perhaps you can apply the scan algorithm twice, and then you get the generalization for free.
Yeah.
All right. So I think this will be perhaps like a good time to pause. So everyone, let's thank like Izzat again. Like, thank you so much. I really learned a lot, and I think you made me really want to go back and like focus on this book chapter a lot more. So Izzat's going to be coming in as well next week on Friday to give us like another lecture. However, we're going to try to find like a better process to deal with spammers. So it'll probably be a Zoom link, but it'll just be like a bit more challenging for random people to get into. So we'll keep everyone posted. And again, big thank you to Izzat. We really appreciate it. Yeah, a
Yeah, my
big,
pleasure.
big
Thank
heart
you
for
for having
Izzat and minus infinity to the trolls. All right. Well, thank you so much. And I think a lot of people in chat agree that this was a very well explained lecture. So thank you.
me. Yeah, my pleasure.
All right. All right, folks. We'll see y'all next week. Bye bye.